Yeah, let's talk about lexical analyzer first. The main responsibility of lexical analyzer is this is the only phase which actually reads the text character by character, which means once this phase is over, you will never see the letters INT or MAX or X or Y. Instead of these every literal, this is called lexeme. In place of every lexeme, you are going to see a token. So for example, int is a token, max is a token, identifier XX. So only at this phase, lexical analyzer is going to read line by line, and its main responsibilities are, one thing is it will eliminate the comments and it will eliminate the white spaces. Even if you try it as interesting work, maybe even if you write the entire C program in one line, there will be no errors at all. You need not write the C program in many lines without giving any spaces in the sense after the line. Okay, between them, you have to between int and max you have to give a space, but then after this you need not give any space. So if you write a program completely without any spaces, then also it works fine, right? So here, coming to this, the main responsibility of lexical analyzer is, first is converting the lexemes into tokens, which means names into tokens. That is first one. Second one is removing the comments. Third one is removing the white spaces wherever you have given extra white spaces. And then only at this phase, since we are reading them character by character, we know what is the line number of each lexeme. For example, sometimes you will see that at some line number there is a syntax error, and this can be done only because the lexical analyzer is actually reading the program line by line. Otherwise, it would not be possible. Okay. So removing the errors, first thing is removing the comments, removing the white spaces, and third thing is, if you get any errors, it is going to show up. And how many tokens are there in this program? So if you count the number of tokens, so int is a token, max is a token, 1, 2, even open brace is a token, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So completely there are 25 tokens in this particular program. Okay, you are not going to count anything of comments as a token, that will be completely removed. So there are 25 tokens. And one more thing is this a valid declaration? Int max x comma y, and then later there is int x comma y outside it. They are not actually global variables. This declaration is perfectly valid, and I suggest that you read that book, the C programming language by Dennis Ritchie. That is the best book if you want to learn about programming more, especially C programming more. That is worth reading. Okay. And next one is, let us say there is a line like this. How many tokens are there in this particular line? So printf is a token, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You are supposed to get 11 tokens, right? But then there are this is wrong. The reason is there are no only 8 tokens in this. The reason is the entire string, this entire string literal, is considered as one token. The entire string constant is one token, and the remaining things are one token, which means one token is printf, second token is open brace, third token is the string, fourth token is comma, fifth token is ampersand, 6, 7, 8. Therefore only 8 tokens are there. So some questions in lexical analyzer is, what is how many tokens are there and what are the responsibilities? That is all about lexical analyzer. Okay. Let's see about syntax analyzer or parser. Before going to syntax analyzer, we have to think about grammars. So the input to syntax analyzer is a grammar, and therefore the syntax analyzer is going to take the grammar. See, if you have a syntax analyzer, you have to give the grammar first and then the input. Now the input will be checked according to the grammar. Therefore, before going to syntax analyzer, let's talk about grammars. And the grammars are like this. Generally, the way we represent grammar is VTPS. So if you are not good with the grammars, or if you have not done automata theory, it is better that you watch my automata videos of grammars, and then I can come back to this topic and watch it. there I will be discussing everything at depth. Here, I assume that you have already watched that video. So even then I just introduce the basics. Grammar is VTPS, where V is nothing but variables, T is terminals, P is productions, and S is the start symbol. Example, let's take this grammar. E derives E plus E, E star E, ID. If this is the grammar, I have three productions. Okay, so generally this is one of the way to represent three productions. You could even write it as E derives E plus E, derives E plus E star E, derives ID. This is one of the ways. Okay. Now here the main variables are nothing but the left hand side. In the left hand side we have only one symbol. Therefore, the set V contains only one symbol E. And the terminals are all the whatever is not there on the left hand side, that is generally a terminal. So in this grammar the terminal is plus, star and ID. Okay, so whatever these rules are called the productions, and the start symbol is one of the variable, and here we have only one variable, therefore start symbol is E itself. So next thing is, once we have considered this entire grammar, what is the output, what is the main purpose of the grammar is they will generate all these strings. For example, if I want to generate this string ID plus ID star ID, if I want to derive this string from this grammar, okay, so it will look like this. E derives E plus E, and then either you could replace this E first or this E first with any of the variables. This is called derivation. I am going to do the derivation, and in this derivation you could derive the first variable in the expression or the second variable in the expression, or in any order. If I go in the leftmost variable first, then it is called leftmost derivation. Let me show you leftmost derivation. Okay, leftmost derivation means I have two variables and I am taking the leftmost one. Leftmost one is the first E. So how can I write it? This one is going to be replaced with ID plus E, and now the second variable E, this one has to be expanded using any of the productions. So the right production is E star E. Therefore I am going to expand ID plus E star E. This E is replaced with EE. Now again we have two E's. So which one do you want to replace? The leftmost one. Why? Because we are doing the leftmost derivation. Okay, now what do I get? ID plus ID star E, and finally the last one, ID plus ID star ID. Now for the same grammar, for the same string, this is leftmost derivation, what we did. Now if I want to do the rightmost derivation means at every point we are going to replace the rightmost variable first. So E derives E plus E, and now what is the rightmost variable? The rightmost E. What do you want to replace it with? You cannot replace with ID, you have to replace with E star E. Now how many variables are there? Three variables. Again you replace the rightmost one first. E plus E star ID. And what is the rightmost one? The second E. E plus ID star ID. And again the last one. ID plus ID star ID. Therefore this is the leftmost derivation and this is the rightmost derivation. Okay. Now my question is this the only leftmost derivation possible, or is there any other leftmost derivation possible? Let's see this. Can I derive the same string using leftmost derivation using the same grammar in a different way? Let's just see this. E derives E. What if I take E star E first? Can I still derive this string? It turns out that we could. Okay, I'll take the leftmost one, E plus E star E. This leftmost one is replaced with E plus E, this production, leftmost one, and again the leftmost symbol is replaced with ID, and next again the leftmost variable is again replaced with ID, and again the leftmost one is replaced with ID. Okay, and next one is RMD. Is there one more RMD possible? It turns out that yes, we could do one more RMD also. E derives E star E, and now the E derives E star ID, and now first E derives E plus E star ID, and again the rightmost E is again going to be derived with ID, and again the rightmost one, which is only one, ID plus ID star ID. Therefore we have again derived it. Okay, so next question is parse tree. Instead of deriving it using the derivation procedure, can we derive it using the parse tree procedure, which means parsing the grammar like this. E derives E plus E, and this E derives E star E, ID, ID and ID. This is one parse tree, and one more parse tree possible is E derives E star E, and then this first E derives E plus E. Therefore this E derives ID, ID and ID. So if you observe this grammar, for a given grammar, for a given string, for a given grammar, for a given string, we got more than one leftmost derivation, and we got more than one rightmost derivation, and we got more than one parse tree, right? Either we get more than one LMD or more than one RMD, which means rightmost derivation, or more than one parse tree. Then we can say that the grammar is ambiguous. Ambiguous in this sense, if we have two parse trees possible, generally parsers will get confused about which one to generate or which is right. Okay, so in these two parse trees, even though the output is showing it to be the required string, the evaluation is different. For example, if I have any input, let us say 2 3 4, which means if I have any input like 2 plus 3 into 4, the output is supposed to be 14, isn't it? Output is supposed to be 3 into 4 is 12, 12 plus 2 is 14. Now if I use this tree, what is the output that is resulting? And if I use this tree, what is the output that is resulting? Just see this. Now this ID is going to be 2, this ID is going to be 3, this ID is going to be 4. Then the first one, this E is nothing but the sum of this expression and the sum of the next expression. If I have to evaluate this expression first, I need the value of this expression, which means I have to evaluate this one first. Therefore, according to this parse tree, the first one which is going to be evaluated is multiplication, and then the next one is addition. Therefore, according to this parse tree, the right answer, this is the right answer, this is right, which will give the answer of 14. If you use the other parse tree instead, which means this is 2, this is 3, this is 4. In order to evaluate this expression, you have to evaluate this expression. In order to evaluate this expression, you have to evaluate this expression first. This is right, readily available. You need not evaluate anything. But this expression you have to evaluate first, which means 2 plus 3 is added and then multiplied with 4. So therefore, here it is going to be 20. This one is going to give you 20, and this one is going to give you 14. So which is right? Therefore, parser, the confusion with parser is when you have more than one parse tree, parser doesn't know which parse tree to use. So most of the parsers, almost every parser except one parser, we shall see it later, will not allow ambiguous grammars. If there is any ambiguity in the grammar, we have to convert it into unambiguous grammars. There are two questions here. How to find out a grammar is ambiguous? There are no algorithms. You have to do it hit and try way. Second question is how to convert a ambiguous grammar to unambiguous grammar. Again, there are no algorithms. Okay, so we cannot know whether a grammar is ambiguous or unambiguous using a direct procedure. You need practice, and then you have to do such methods. What? Take a string and then check whether we generate 2 or more parse trees. If you get 2 or more parse trees, or if you get more than one LMD, or if you get more than one RMD, then the grammar is ambiguous. In these lectures, I am going to follow the method of parse trees. So in order to find out whether a grammar is ambiguous or not, I'll take the grammar and I'll take a string, and then I'll see if I get more than one parse tree or not. Okay, let's see some examples to find out whether the grammars are ambiguous or not. Let's see 3 more examples whether the given grammar is ambiguous or not. The given grammar is S derives AS, SA or A. So in order to find out whether it is an ambiguous grammar or not, there are no algorithms, which means ambiguity problem is undecidable. We don't have any algorithm for that. So only one thing is you have to try and see all possible strings. A grammar is said to be ambiguous if for any string which is derived from this grammar we get more than one parse tree. So for example, if given this grammar, tell me string which is generated by this. I'm guessing that the string AA might give me more than one parse tree. How do I know it? I'm just guessing it. There are no direct methods. Okay, so as derives, I'm just trying whether we get more than one parse tree or not. This is one parse tree, and as derives, yes, and this is one parse tree. Yes, we got two parse trees for the same string from the same grammar. Therefore, we can say that the grammar is ambiguous. The grammar is ambiguous. You can even try with two LMDs or two RMDs, but then maybe you might have to try with a different string. Yeah. So next one is whether this grammar is ambiguous or not. For that, you have to again do the same method. What is the method? Guess the string, some string, any string, and then see if you could find more than two parse trees. If you are lucky, you will find it for a small string. Otherwise, you have to keep on doing. That is why there are no algorithms. Okay. So the word is, let us say AB, AB. If this is the word which we want to generate from this grammar, let me see if you get more than one parse tree. So one is as derives A, yes, B, yes, and now this one, this second, this as derives B, yes, A, yes, and this one is epsilon, this one is epsilon, this one is epsilon. When you have such a big parse tree, sometimes you might get confused about what is the output of the parse tree. Now that is also called as yield of the parse tree. For that method, you have to traverse the tree top to down, left to right. While traversing the tree, whenever you come across any terminal, you write it down. Then you will find out what is the string generated by this. Traverse it top to down, left to right, which means like this. What is that you have encountered first? A, and then B, and then again A, and then epsilon. I am not writing it because epsilon is not going to be any value, and then again B. Okay, so therefore that is AB, AB, right? So let's see if we get one more parse tree. Just let's try. As derives A, yes, B, yes, and let us expand the second S first. Here I expanded the first S, here I am expanding the second S. I am expanding the second S with again AS, BS, and this S with epsilon, epsilon, and epsilon. Now just see the yield of this. Yield of this is, first you encounter A, therefore output of this is A, and then you encounter epsilon, so don't write it, and then you encounter B, B, and then you encounter A, yes, and then you encounter epsilon, leave it, and then you encounter B. Therefore output is AB, AB. So for the given grammar, for a given string, we got more than one parse tree. Therefore again this is ambiguous. Okay, so let's look at this example. So what is this example? R plus R, R star. It is nothing but a grammar which is representing all regular expressions. For example, this R derives R plus R is nothing but a regular expression can be union of two regular expressions, or concatenation of two regular expressions, or a clean closure of a regular expression. And a regular expression can be either A or B or C. They are primitive regular expressions, right? So how do I get more than one parse tree? It is same. Maybe if you want to generate A plus B into C, like how you generated it for A plus B into C there, A plus B concatenated with C, I get two parse trees. We have already seen such a model. RR, BC, and then A. Here this concatenation is getting higher precedence because it is at the lower level, right? And let us say one more, R, or let me say this is RR, and then this one is R plus R. Again it is A, B, C, which means one expression is computing B into C first, and the other expression is in the other parse tree is computing this first. However, we got two parse trees, therefore we can say that the grammar is ambiguous. Okay, So all the three grammars are ambiguous grammars.